Okay, hold on for a second.
No problem. As always, everyone, this session will be recorded and posted on our website at pragmaticworks.com under past webinars. No problem. Bear with us one moment, everyone. Our session.
So I should be ready.
Okay. All right, I can see your desktop.
Okay, good. And let's start.
Great.
Welcome, everyone. I hope everyone can hear me. My name is Michael Rees. I'm a program manager in the SQL Server Engine team. You can see here both my pictures, since you can't see me while I'm talking, and also my Twitter handle in case you want to get in contact with me at a later time. Today my topic is talking about performance and scale of beyond relational capabilities in SQL Server 2012. But before I actually go into that topic, let me give you a quick overview what actually beyond relational really means and what we are trying to achieve. So if I look at my favorite beyond relational application, I can use Outlook as an example. Why is that a beyond relational application? Well, it is managing both structured data, such as the header information inside my mail, as well as unstructured information, such as the context of my mail messages, the attachments, etc. And in addition, it provides a set of interesting capabilities over the data that I store inside my database, or in this case, inside my Outlook file, such as, for example, the ability to do structured and unstructured search, and have the ability to do related searches, like what I would consider to be semantic related searches. Although in the case of Outlook, it's very simply based on either messages that have the same sender or messages in the conversation. But you could imagine that they might find related documents based on some semantic analysis. So now if you build an application like that, unfortunately what you have to do is you currently, if you use a database to store the information, or if you use a file system to store the information, you basically always have to build these capabilities yourself to build it, to provide these services. So the goal basically is that we can provide you with certain services built into the data platform, so it makes it easier for you to build applications like these. So to kind of look at the pain points that you have, if you have applications that have relational and non-relational data, it's often hard. You have to build your own complex integration at the application tier. You have to duplicate functionality because they are not integrated. And if you, for example, have something like storing your files inside a file system and storing your structured data inside the database, you will have to compensate for unavailable services. Like, for example, you will have to build your own backup restore solution for the data that lives inside the file system that it somewhat integrates with the backup restore solution that you do for your data inside the database. So our goal is basically to reduce the cost of managing all this type of data by simplifying the development process, as well as giving you unified combined management and programming services for all the types of data inside the data platform, so you can make use of it when you're building your application. So what is the beyond relational mission that we have with SQL Server? Basically, the first thing is that we give you the ability to efficiently store all types of data, not just tables, but XML, spatial, documents, etc., etc. In addition, then, once we give you the storage, we also give you certain guarantees about the ability that we can process that type of data. And we give you these capabilities for all your applications that you want to build on top, such that we, for example, understand the data format natively. Like if you give us a spatial object, we actually know it's a spatial object and we can do things that you expect us to do with the spatial object. The ability to give you a well-known API for putting files into the database, etc. And then finally, we give you rich capabilities and services over all that data, such as the ability to query over the data, to have search across the data, and have integrated manageability aspects such as integrated backup restore for all types of data. So that's kind of what we are trying to do with Beyond Relational. Now, it's not a new story. The last non-Beyond Relational or truly core relational SQL Server instance or version was SQL Server 6.5. And in SQL Server 7.0, we added search and unstructured data management. And then over the last couple of releases, we added a lot of capabilities such as, let me hide this here quickly, if that is possible. Yeah, so, and we have the ability to basically now manage unstructured data, give you semi-structured data support, give you XQuery for managing XML, we give you spatial indices to manage spatial data, etc., etc. Now in SQL Server 2012, we added a few new capabilities, and the ones that we are adding are, first, the ability now to actually manage your unstructured data not through a specific programmability layer, like we had with SQL Server 2008 and Filestream, where you had a specific API to access it, but in addition, we also give you the ability to manage it directly. And we added a new kind of capability around semantic search that I will be quickly mentioning later in the presentation as well. So just to tie back, we have efficient storage for beyond relational data, we have the rich data programmability capabilities, and we have the services in form of the operations, in form of search, etc., over the data itself. Now in SQL Server 2012, we are focusing primarily on kind of two or three things. One is that we are looking at rich unstructured data management, where we worked on scale-up for storage and search. We improved our access story to unstructured data from all applications, including applications that already exist, and give you rich insight into the unstructured data to make better decisions about what the data is about. And we also deliver more capabilities around building spatially aware applications, such as adding more 2D spatial capabilities, add spatial support in other components in the platform, and improve performance and scale as well. And last but not least, we also did some work on Service Broker, which is our messaging platform, by adding messaging broadcasting, which allows you to have a more performant way of distributing your messages to multiple recipients at the same time. Now, in this presentation, I'm not going to go into details about the functional aspects. For that, I have a list of links to presentation and webcasts at the end of this presentation. So you should be able to go and get some more insight into the details on each one of these points. What I'm going to focus in this presentation is primarily around performance aspects and scale aspects for these two topics around rich unstructured data and spatial support. So let's first look at rich unstructured data performance and scale. Our goal was that we can scale up storage and search to 100 million large to 500 million small documents at least. Now this is not an upper bound. This is just what we basically made sure that we would hit. Now, with, of course, the understanding that if we are hitting that goal, given that we have enough hardware and can scale up more, we should be able to go up and further up to higher numbers than this without big problems. We also worked on, and some ways of achieving that was, for example, that we provide you the ability to have multiple containers for storing file stream data instead of having to manually partition your data across multiple locations for your file stream. We also improved scale up for search, and I will go and show you that in the remainder of this presentation. Let me quickly give you kind of an architectural overview, though, about how we are actually managing our unstructured data in SQL Server 2012. We have at the beginning the database, of course, where we are keeping all our transactional data. Normally it's stored inside tables. I can add data into blobs, var binary max, as well as part of a table inside a cell. However, if I do that, I have to basically make a decision between streaming Win32 access or integrated administration. If I keep it in the table, I get integrated administration, but I don't get streaming access to the data inside the blobs. And if I want streaming access inside the data inside the blobs, I used to have to basically put it out into a file system and then have to put a pointer into the table and then manage everything around the administration aspect and consistency, etc. myself. So in SQL Server 2008, we gave you the ability to put blobs into a file stream. Now, a file stream programmatically is nothing else than a hint on my column that the var binary max data is stored inside the file stream environment. Now, the file stream environment is managed as a file group inside the database, and what it basically is, it's a location under the control of SQL Server that is nothing else than a directory that contains all the blobs, each one as a separate file. Now, in addition to storing it inside the file system as a file, so I can get streaming access against the data and get integrated administration, I also give you specific non-SQL APIs in addition to give me the ability to basically build Win32 applications that just use the file stream API to access the data inside the files. Now, that file stream API is transacted, which means I actually cannot use the standard open file. I have to use an open file that knows about the transactional context, which we provide as part of our extensions. So I still didn't have the ability to take existing Windows applications, for example, and run it on the blobs that I store inside the database. Another thing that we have added in SQL Server 2008 is the ability to have remote blob store access for really large amounts of data that we store outside. If you consistent API against any one of these blob stores, be that up in Azure, for example, inside Azure Blob Storage, or Centera, EMC, or Fujitsu Nearline, or even another SQL Server instance that uses the database. And this is actually the API that SharePoint is now using for storing its unstructured data. Now, remote blob store APIs doesn't give us full consistency and full integrated capabilities like search, but it gives us an additional ability to manage more loosely coupled unstructured data. Now, in SQL Server 2012, we added now the ability to take your Windows applications and basically just operate on the data inside the database directly. The way that we did that was that we added a new concept, which is a file table, that gives us the ability to expose the content of the file inside the database as a set of files and folders using an SMB share interaction. So you basically have now a path into the database where you can put your files in, and you can do transactional relational access to that table, to that file table, as well as doing your standard Windows application. So you can open an Explorer, for example, a Windows Explorer shell, and drag and drop data in and out of the database, for example. In addition, as I mentioned earlier, we give you the ability now to scale up the storage of these file streams, and I will get into that in a little bit more detail later. And we give you rich services such as semantic similarity search, which again, I'm pointing you to the other presentations for more details that I'm listing at the end. And we worked on additional capabilities in full-text search, One of the major improvements there is around performance and scale. So I'm going to go into that aspect again in the remainder of this presentation. So just here is a quick overview of what a file stream is, because that's kind of the core of storing these blob data. The important aspect here is really that it stores the files under the control of the database, but inside a file group that is basically keeping each blob as a separate file. File table then is building on top of that, and it's a very specific table format that you can create that then adds additional information so that it exposes the content of that table basically as an SMB share, so you can navigate down using your standard Windows 32 file APIs. So in terms of once you set up your file stream file table, there are a couple of performance tips that I have to share here. One is that if you have bigger buffers to read, then normally you get better streaming performance. And many of these things are actually standard file system kind of performance tips. If you have a file stream or file table data and put that into a volume, into a file group, then make sure that that volume on which that file group is hosted should have the 8.3 and last access time capabilities disabled, because they are normally limiting the scalability and performance of storing files in large amounts. Also, like any file group, you probably want to have it reside on a dedicated volume, separate from the log, separate from your relational data, to improve your I/O parallelism. And when you have one volume per file stream file table container, then you can do space management at volume level. You can do set your SMB buffer sizes to a good size. So, for example, 60K or 480 kilobytes, we found out are good performance buffer sizes that you can set at the volume level. If you want to do partitioning your file stream data, you should use a row GUID unique index to do aligned partitioning. You should turn off your antivirus programs, or basically better configure it to quarantine data, because they normally come in at a very low level and might be doing both performance and consistency violations of your file share. And if you're using compressed volumes, a cluster size of 4K has been seen as a cluster size that seems to be working well. Of course, you might be able to tune it a little bit more by understanding your exact compression process and your volume capabilities, etc. So if I look at when I store data inside my file stream and I have a lot of reads on the data, then there is a kind of cutoff point between storing the data inside a var binary max column that is just var binary max, as well as storing it inside a file stream column. And basically what we see is that if I read the file stream through the file system using the either the file table APIs or the file stream APIs, then starting at about 200 kilobyte file sizes, it is better for reading performance to have the data inside a file stream. If I put the file stream data into a file stream column and then I access it using T-SQL, the cutoff point is around 1 megabyte. Well, why is that? Well, the reason is that while I have streaming access, every time I open a blob inside the file stream environment, I open a file and I close a file. So there's a little bit of an overhead there by having to do open file, close file, because if I have the blob stored inside the database, inside a normal var binary max column that is not file stream, then I already have normally opened the MDF file in which the blob resides, so I don't have that overhead of having to open files and close files all the time. Now, so the trade-off there is that I should have a certain understanding of the size of the data before I make the decision between storing it inside file stream versus var binary max without file stream. Now, this is just for performance purposes. There might be additional reasons why you want to have the data inside a file stream, like inside a file table, which you might want to store smaller data there as well. For example, if you want to have the programmability experience of just using an existing Windows application, then you use a file table, even though it might be more efficient in keeping the data inside the non-file stream environment. So you can see that for reading, depending on what API you take, the kind of cutoff size that we recommend is about 200 kilobytes or 1 megabyte. If I have a lot of writes, then the cutoff point is a little bit higher. The cutoff point is basically slightly below 2 megabytes in file sizes. Now, these two numbers have not changed between SQL Server 2012 and SQL Server 2008. The performance got better, the throughput numbers got better, but the cutoff points are about the same. So what did we do in SQL Server 2012 to improve the performance? Well, the first thing that we did was we added the ability to have your file stream data now stored in multiple containers, or basically multiple file groups that are distributed across volumes. So in SQL Server 2008 and 2008 R2, you only had one storage container per file stream group, which basically limits you to the scaling that you get within a single directory, so to speak. Now in SQL Server 2012, we give you the ability to have multiple storage containers per file group, which you can set when you create or alter a database. You can set max sizes for these containers as well. And this gives us bigger scaling flexibility because we can just add additional storage drives to a file group and therefore kind of scale out the processing or scale up the processing by having multiple spindles and I/O parallelism. So here's an example where we basically compared the green line is the kind of throughput I can achieve using overriding the blob using 1 megabyte buffered writes. And if I have a single table with a single container, that's kind of the situation I have in SQL Server 2008. And you can see we scale up to about, in this case, 220 writes per unit in this context. And now if I, in SQL Server 2008, wanted to model a kind of a scale-out thing, I had to take my data and manually partition it into two tables, and then each table would have its own volume for its file stream data. And you kind of see the blue line. Disregard the downward spikes here. That's some weird anomaly that we got when we were measuring the data. And but you can see that by adding another volume, we are now basically getting the double throughput of processing if we increase the number of processors to write the data. Now in SQL Server 2012, we can now have a single table with one file group where we have two containers distributed across two volumes, which gives us the red line, which you can see gives us the same kind of scale up with respect to write performance against it as we have if we actually do a manual partitioning against two volumes. So we can see that we are actually getting almost linear scale up for our writes by adding additional containers to storing the unstructured data. Another thing that we're doing was we actually improved the throughput of our T-SQL and file I/O access. Now, as I mentioned earlier, the cutoff points for the sizes, the recommendations are still the same, but we increased our read throughput by about a factor of 5, and we have improved our scaling capabilities against a larger number of concurrent threads. So you see kind of both a normal read and SND loopback read, and you see the throughput numbers. The lower line is the line that we achieved in SQL Server 2008, And you can see that for increasing number of concurrent threads up to about a thread of about 1920, you see that we are actually having a factor of 5 to 6 times as fast in the read case, and then afterwards contention kind of kicks in, and we are coming down again with respect to the throughput. But we are definitely improving our read throughput tremendously with normal code maintenance and improving our code paths for doing file I/O, both in T-SQL and using the Filestream APIs. So once we have improved our performance in storage, another big kind of performance improvement that we looked at was around the search services. So in full-text search, we basically looked at being able to scale up to these 100 to 500 million documents, depending on size. We are also looking at making our full-text query performance about 7 to 10 times faster than what we had in SQL Server 2005 and 2008, and that we had a test corpus for which we wanted to make sure that the worst-case query response time was less than 3 seconds. And of course, we are always kind of comparing ourselves also against some of our database search competitors. Besides improving performance and scale, we also added new functionality, which I'm not going to go into more detail during the presentation. So what did we do? There were lots of code internal implementation details that we improved. A few things that we did that are easy to explain, besides that we reorganized the code and did improvements to algorithms, is that, for example, queries, full-text queries, no longer block index updates. So previously, apparently, a full-text query often was taking a lock that was blocking index updates. Now, in SQL Server 2012, we improved that. We also did lots of improvements to our query plans so that we get better plans for certain common queries. We are folding full-text predicates, which can improve performance in more complex predicate cases. And we now give you more parallelism around executing the plan, which is helping you with the performance. So what we did was we had a couple of customer workloads and synthetic workloads that we used to test our performance work. And we basically achieved an index and query testing to up to 350 million documents, of course, on a appropriately scaled up in hardware environment, where we achieved less than 2 seconds response times for all the queries and etc. that we tested. We were about 3 times better when there was no updates running, and up to 10 times better with the background updates running in terms of throughput. So that basically means we are kind of achieving one of the goals that we had of about up to 10 times faster. And we also scale more easily now with an increasing number of connections. So let me show you some measurements that we did. In terms of throughput, one of the kind of vexing problems that we had with SQL Server 2005 and 2008 was that when we had queries and increased the number of CPUs, we actually didn't increase the throughput of our queries. So that means we actually didn't scale against multiple CPUs. So by adding our changes and parallelism, etc., now with SQL Server 2012, you can actually see that we are getting a really nice scale up by just adding additional processors. So we're actually increasing our queries throughput tremendously. These were numbers that we tested over that 350 million document database and having random DMLs running in the background. And so you can see that we are basically getting a scale factor of more than twice and have an average 60 times better throughput for this environment. Now, another thing that people often noticed when they were using full-text search with 2005, 2008 was that if you increased your number of connections against your database doing full-text search queries, your average execution time basically increased dramatically because of internal locks, etc. So what we did was, and then eventually after about 1,000 connections, at least in kind of this particular customer playback scenario, basically you didn't get any responses anymore after like about 1,000 connections. So we did vary the numbers between about 50 and 2,000 users for this test on this specific customer playback benchmark. And as you can see, the red line is SQL Server 2012. And now we are basically scaling up much better under load of more connections. The performance average execution time per query stays much lower than it was before, and we're actually still able to serve your connection with reasonable response times, etc. So definitely another improvement on full text search to give you better scalability for your query loads. So now that we have finished talking about our capabilities of scaling unstructured data, I would like to switch over and talk a little bit more about our spatial performance improvements. Maybe I will stop here quickly and see if there are any questions that people might have.
Hi, Michael. At this point, we don't have any questions.
Okay, good. So I will continue then.
Great.
So a couple of, sorry, I heard somebody.
Oh, I just said great.
Okay, good. So let's take a look at the spatial aspects. We introduced spatial support in SQL Server 2008, and I will give you a quick overview first of what we did in terms of improving our spatial performance, and then I will go and give you a quick recap of how spatial indexing works, and then I will go into more detail and show you some examples of what we actually did in terms of performance. So we added support for persistent computed spatial columns. So in SQL Server 2008, you could only compute the columns, but you couldn't persist them. We also added a new Spatial Reference ID for geodetic data that gives you faster calculations if you don't need full WGS 84 support, and I will go into that a little bit more in detail later so you understand what that exactly means. We improved our internal implementations of operations such that spatial index creation for point data is about 4 to 5 times faster. Our point data queries in general will be faster. We optimized our SD buffer operator, also reducing the memory footprint that it's needed. And all these implementations around, or improvements around operations should lead to faster secondary filter steps in our index access. And I will, what that means, I will explain later as well. And we also improved our default spatial indexing scheme and added a new kind of query window brick density hint for our queries, and I will show you an example of that. We added spatial index compression, and we improved our ability to detect and to utilize indices for certain types of queries. We do that for so-called nearest neighbor queries, and we also optimized our spatial query plan for some distance and intersect-like queries over the ones that we already supported in SQL Server 2008. So let's look a little bit more detail about how we do this and what are the results. So here's an example of how to specify a persistent computed column. Now the benefits of a persistent computed column should be obvious. Instead of having to recalculate the column every time I access it, the result already has been pre-computed for you. So you basically, when you access the data, you can just read it from the disk, and you don't have to run the potentially more complex calculation every time you do the access against the data. So that's kind of obvious. In terms of spatial reference ID, let me give you a quick overview of what that actually is. So each spatial object has a spatial reference ID. The spatial reference ID is similar to a locale information for a spatial object. So what it does is it basically determines what is the coordinate system that is being used. Like, is it a Cartesian coordinate system? What type of projection semantics do I have if I have a geometry flat type? Or what type of geoid dimensions do I assume if I have a geodetic geography type? what are the units of measurements, like is it in feet, is it in elbow length, is it in meters, etc. Now, in SQL Server 2000, only 2008 and 2012, only objects of the same SRID can be operationally combined. If I try to do an intersection between two different SRIDs, I will get a null value back. Now, the defaults are set to 0 for the geometry type, which is not really having any implications on the way that the operations performs, because the geometry type is a flat earth type, and basically Euclid, the Euclidean geometry, Pythagoras, etc., all these standard geometry algorithms apply regardless of what your SRID is. Now, this is different in the case of the geography type. The geography type assumes that your data lives on top of a geoid, and depending on what your assumption is about how stretched or how specific that geoid surface looks like, your operational semantics is actually quite different. And if you have something like WGS84, which is the SRID that the latitude, longitude of GPS devices assumes, then you have to understand that this implies certain calculations to give you, for example, distances or the size of the area of a polygon, etc. Now, this impacts operational semantics, and so therefore it impacts the performance of these operations. We have 390 predefined SRIDs based on the European Petroleum Survey Group list, and there's a built-in catalog view that allows you to actually look at them. And in SQL Server 2012, we added an additional Microsoft-specific SRID with the number 104,001 that assumes that the globe is a complete spherical globe, but not a geoid that is like flattened at the poles or anything like that. Now, by doing it, by providing you that SRID, the operations for things like area calculations and distances, etc., become much simpler on a spherical globe than on these geoids. So that gives you a certain ability to improve your performance of spatial operations if you are fine with that simplified assumption of how the geoid looks like. As an example, for example, the data that you have in Bing is, for example, assuming that you have a spherical globe. So it's actually simplifying the assumptions about how the Earth looks like. So now, after talking about some of the things that you can do by just using spatial data differently, now let's look a little bit about how we actually affect performance in the spatial indexing context. And before I do that, let me quickly give you a recap of how spatial indexing works for those people that are new to the area or kind of just use indices without knowing what happens behind the scenes. Now, spatial indexing is a little bit different than the standard relational indexing because the data that you're storing is much more complex shaped. It's not just the point that you can say I'm either bigger than the point, equal than the point, or smaller than the point. It's now a multi-dimensional kind of comparison that I have to do. So if I have a set of geometric objects like the 5 forms that you see here on the screen in blue, now if I come and query it and probe it with, for example, an object and say, which of these objects intersect with my red diamond? I now have to basically do a little bit more complex processing. And in general, what we do is if I have a query and if I have a spatial index, I split the query predicate for the spatial predicate into 2 steps. The first step is that I do an approximate lookup in the index to give me candidates of objects that might be intersecting. Now, this index lookup is designed to be very fast and to make sure that I don't miss any objects that could be a candidate, so I'm not having any false negatives, but it might give me false positives as a result because I'm not doing exact comparison, I'm doing a grid level comparison. And so if I do that, then of course I have to take the second step. And the second step basically is what we call the secondary filter, where we apply the original predicate to give the actual true result. Now that original predicate is what we call the secondary filter. Now that performance, or that time that is being spent in the secondary filter, is directly proportional to three things. It's proportional to the number of false positives. It's proportional to the cost of the operation to do, for example, an intersection exactly using our CLR code. And it's proportional to how many optimizations we can do so that we don't have to apply the secondary filter. And that can be, and I will explain some of that later. So we can actually do some tweaks to the scheme to not have to apply the secondary filter under certain circumstances. Now, so as you can see, it becomes quite interesting in terms of how to tune the index to reduce that secondary filter time, and I will show you some examples of how you can do that later in the presentation. So let's look at what we're actually doing when we store an index, a spatial object. So let's assume I have this complex olive-colored polygon that you kind of see in the back. And what we do is we basically take the object and tessellate it into cells. Tessellation basically means that we take a two-dimensional plane and we basically put grids on top of it. And then for each one of those grids, we basically store it inside a row inside the index. So if you have 64 cells per object, you can see a very approximative representation of the object. And the more cells I have, the more precise my kind of shape becomes, follows the shape of the actual object. But the more data I store inside the index, which means I will have to read more data out of the index. The other interesting part is that the cells are actually two types of cells. There are those cells that are completely covered by the object. They are blue in this case. And then we have the cells that are containing parts of the object, but they are not really completely covered by the object itself. And that's interesting because we can make use of that knowledge to avoid having to run the secondary filter. If I do an intersection and I know that one of the cells that I find inside the index for the object is one that is completely covered by the object, then I know that every other object that lives in that cell is going to be covered and therefore intersecting. So I don't have to do the secondary phase of comparison, so I can avoid the secondary filter step. So that means the more precise coverage I have for my object using these covering cells, the more likely I am to not have to apply the secondary filter. So that means there's a trade-off between how many rows I have in my index, given by the number of cells that I use to tessellate, versus the reduction of processing I have to do because I can skip my secondary filter step. So it's a very interesting kind of thing that I have to kind of look at. So if I have my fully contained cells here, then I might get better performance. So when we defined the index in SQL Server 2008, we basically gave you one mechanism of giving you 4 grid levels with different grid densities that you can specify to kind of tune your spatial index. Now in SQL Server 2012 we add a new spatial index tessellations that we call the auto grids. Now the auto grid uses a fixed 8 grid level instead of the previous 4s, and there is no grid density parameters that you can set. We basically just have it fixed at a specific setting and set a specific default numbers of cell per objects for the index that you can go and still override. Now, the reason why we introduced this index was that it gives us more predictable and stable performance for windows of different sizes and for data with different spatial properties. So for the default values, we are often up to 2 times faster for longer queries. by having more efficient primary filters, and we return fewer rows basically as part of the primary filter. However, we will be a little bit slower for very fast queries because the increased tessellation time that we have for probing, for tessellating the probing object will be bigger than in the other case because, of course, we have more levels to tessellate against. Now, here is kind of a comparison of the new index compared to the old default index. And the reason why this is an important thing is that most people start out with the default index without going and tuning the index appropriately. And so what that means is that you want to have the default index to have a better kind of predictability in terms of being a rather good index. It might not be the best one, but it should be more predictable than, for example, the blue line, where you see that in some cases we get pretty good performance, and in other cases we might be like getting a very slow query because the data is skewed in a way that the default index doesn't give us a good performance. Now, the new auto-grade index gives us a much better kind of predictability and variability in terms of the peaks that it might get by running these different types of queries. Now, it doesn't mean that the grade index is always the best index. There are still cases where, of course, a finely manually tuned index might still give you a better result than the default, but the default is much closer to the optimum than before. So let me give you an example of some spatial queries here. I'm here connected to SQL Server 2012, and I have some data here that contains data about H1N1 bird flu cases that were all the rage a couple of years ago. So here's a table. You can see it's a normal table that has lots of relational data. And at the end, it has a geometry type column here that gives you points on where these data actually has been reported. So if I switch over here to the Spatial Result tab, you will see here there's a couple of points here, and it kind of looks like the outline of the US here. So each one of these black dots is basically a case. And I also have a table here that contains the counties of the United States. Again, you kind of see lots of relational data here plus a spatial result. And you kind of see that now we basically have each one of these counties being a polygon represented spatially. So now what I want to do is I want to basically do a spatial join between these two data sets. Basically, the query that I write here is first I get myself all the counties and population and name information from counties where the state name is equals Washington. So I basically get me the counties for the state of Washington, which kind of looks like this. In addition, I then do a join between my counties and my H1N1 data for all the counties that are in the state of Washington that intersect with these dots. So if I run this query, and I do a union here to give you a certain visualization, you will notice that the query is running, and it's taken quite a bit of time to actually get us a result. I think it's about 20 seconds, so a little bit more. It's actually taking even longer than that. So let's just stop it, and I don't know, it's down 26 seconds. And here's the result here. So you see the dots where N1 cases have been reported in location to the counties of the state of Washington. Now, if I look at the query plan, you would notice there's no really spatial index involved because there's no spatial index defined. So since these are geometry data, I will now create a geometry index on this data. And what I will do is I will use a bounding box that I have to specify for the geometry type that is basically covering all the counties in the US, because maybe my queries in the future might want to be also querying against other states, not just Washington state. So in order for having that, I first need to get my bounding box. So here in this query here, I basically calculate the bounding box for my US data. And so I take these coordinate points here and add them to my spatial index. In addition, since I know that the data that I'm indexing here on H1N1 is point data, I set the grid density to high to improve the kind of precision into which I can identify which cell that these indices, that these points are living in. Because it's a point, I always only get one cell, one entry per point anyway, so I can have a high grid density here in this case. And so I create that index. You see the index was actually quite fast. And now if I run the query again, this is the same query, and let me add the query plan here to kind of show you that we're actually using an index. And now the query is executing, and it is done now in less than 3 seconds, and you can see the query plan looks very complex. And down here you see that we have clustered index equals spatial that we are actually going against. So as you can see, spatial indexing actually gives us quite a bit of ability to be faster. Now, I mentioned earlier that there's a trade-off between the primary filter and the secondary filter time. And that trade-off is not only steered by how I index the data, but also every object that I have inside my query that I have to probe against the index, I have to do the same tessellation. And in SQL Server 2008, we had a fixed cell for that, fixed numbers of cells for that query window. However, it is an optimization problem here. The more cells I have for my query window object, so in this case, in the earlier example, every one of those shapes, polygons representing a county was being used as a query window probing the index. The more cells I have for that probing, the less time less time I'm actually spending on potentially doing as basically filtering, etc. So there's a little bit of a local minimum that I have to find. And in SQL Server 2012, we give you the ability to hint that that number so you can optimize it, so that we can actually reduce the times needed to process false positives or process lots of primary filter time because I have a really big index that I have to join against. So the default values for these probing windows are given, as you can see here, but we can actually override that. And we can override that with a spatial index hint that is spatial windows max cells that we can specify in a query. Note that this is only used if an index is actually chosen. It does not force an index by itself, so you would have to use an index hint to force an index if you want that. It overrides the defaults, and the rule of thumb is that the higher the value is, the longer the primary filter phase is, but it reduces work in the secondary filter phase. And it's going to, so if I have sparse spatial data or point data, etc., then setting it lower might be better because I actually have less data that I have to go and join against. So let me show you an example of that in here as well. Let me scroll down here a little bit on my data here, and let's see where it is. I think here we are. So if I take the same query that I had before, you notice that it took us about 3 seconds to run the query here. Actually, we can improve the time even more by setting the spatial windows max cells to a lower number. Well, why a lower number? The data, as you can see here, is pretty sparse. There's not too many data points inside each one of these cells. So that means that if I have a much smaller probing window, I'm actually going to have a much faster primary phase to execute on. So let me run this query here. And you notice that now the query suddenly returns in less than a second. So it actually can make quite a bit of a difference. So with having an index and with this spatial windows max cell, we went from 26 seconds for our spatial query to basically less than a second in response time. So another thing that we allow you to do in SQL Server 2012 is to compress the spatial index either using page or row compression. We did some internal tests with compression, and the result is that normally the indices are about 40 to 50% smaller than without data compression enabled, and queries are between 20% faster to 15% slower, depending on how much we gain by having less IOs compared to how much we have to spend in addition to do the decompression of the data. Just as a note, the partition compression setting is not supported, so you either compress all the partitions in an index if you have a partition index or none. Additional work that we have done around query processing is that we do a better job in supporting index intersection, and we have been doing for a while a couple of interesting matchings for our index. In SQL Server 2012, we are now matching nearest neighbor type queries with an index, and in 2008 and 2012, we basically take distance queries and convert them to intersections so that we can use an index. We understand that A intersects B is the same as B intersects A, so we actually understand commutativity of the operation and use the index regardless of how you formulate the query, which is different from some of our competing database vendors that are requiring you to have the index on the outermost of the two objects, which, of course, since the operation is commutative, is not really very user-friendly. The same goes for duality, so I know that if A contains B, then B is within A, so I can also make use of the index regardless of which ones of the two columns are indexed. And I can have more than one spatial index on the same column, which gives me the ability to basically have an index and then force the index for specific, for example, query windows, etc., or different granularity expectations if the data looks a little bit different in different places. And as I mentioned, the outer reference as a window object gives me the ability to use only one index during the spatial join, which is actually often more efficient than having to use both indices. So let me go and show you to the end now what we can do with spatial nearest neighbor queries. So the main scenario here is give me the closest 5 Italian restaurants. In SQL Server 2008 and 2008 R2, we basically got a table scan with that query. And in SQL Server 2012, we used the spatial index. However, you have to use a specific query pattern. The query pattern is basically that you have to use either the top expression or the new fetch first rows that we are supporting in 2012. And you have to have an order by position, and you have to make sure that the distance is not null, is in the predicate. That last part is important because unfortunately SQL Server orders nulls first, and so if you have a few nulls because of null values or mismatching SRIDs, you would actually end up getting the nulls first. And so we kind of require you to say is not null because I'm assuming you don't want to see the null values there. Okay, so if I do this nearest neighbor query, here I show you an example where I have data from earthquakes all over the world. There are about 15,000 earthquakes data that I have. And I take here a point that is Seattle, and I would like to find the 20 closest earthquake, their magnitudes, and the actual point from Seattle. So if I run this here, you will notice this is one of these nearest neighbor queries, and you will notice it's taking me a long, long time. So I'm kind of stopping that query right now. Or it's actually, okay, it's done after about 8 seconds. And if I look at the plan here, there is no index here. It's just an index, a standard scan over my data. So what I do is now I create my spatial index. And in this case, I just use the new default index. Takes a little bit. And now I can run the same query, but this time I have the index. In this case, I actually hint the index as well, and you will notice that my result is now about a second, and the index is actually being used because the query plan actually is much more complex here. So as you can see, we are now able to detect these nearest neighbors queries. And as you can see here, we did some tests with against our current suggested workaround, which says take the points within a certain radius, sort them, and then chop off the top numbers of those. And you see that our new query plan is much better if you have high-density points that you have to look at. So, for example, if you look at here, the New York Central Park has, of course, a lot of businesses in a 10-kilometer distance. So, therefore, the query that looks for all the businesses in 10 kilometers and then sorts them is going to be much worse in performance than our nearest neighbor query plan. But if you have very sparsely populated environments within the 10-kilometer distance, like rural Idaho, for example, then of course the performance is about the same. Okay, there are a couple of spatial tips I would like to give on index settings. I would recommend that you start up with the new default tessellation. Then point data, use the standard one with all high sets, and cell per object is not important. If you have simple relative consistent polygons and you are not satisfied with the default tessellation, try setting all levels to low or medium, medium, low, low. If you have complex line strings or polygons, normally a high number of cell per objects is better because it gives you that more precise look into the data. And if you have really high variable sizes, experimentation is needed, and you might want to have multiple indices that you hint. And there's a rule of thumb, or ETS rule of thumb, for geography type. Now, if your spatial query is slow, make sure that you're running anything after SQL Server 2008 SP1, of course, preferably SQL Server 2012, given the improvements we have done. Make sure that the query plan is using an index. If it's not, make sure it's a supported operation. Maybe hint the index if it's still not getting used. There are some cases where you might want not to use a spatial index if you have a highly selective relational predicate, for example. And basically, we have a couple of index support procedures that allow you to assess the effectiveness of the primary filters and the internal filters to see how to tune your cell per objects, etc., or change your bounding box for the geometry type. All of that is being described in the presentation that I linked to at the end here. So there's a couple of additional links here on slideshare.net that have some more detailed presentations talking about the new capabilities, etc. There's also a launch video that talks about unstructured data, etc. And down here you have additional information, my Twitter handle again. For spatial data, I also give you Spatial Eds or Ed Kadibas Twitter handle. He's our other spatial expert. And a couple of links to blogs, although I have to be saying that I haven't been blogging recently too much. So it's probably better to go and use Ed Kadibas blog if you're interested in spatial data. And with that, I appreciate your patience and your interest in the presentation. And I'm sure that we still have 1 or 2 minutes for additional questions, Rachel.
Yes, actually we only have one question, and it is, are these SQL scripts posted anywhere? Is there anywhere for our audience members to get them?
I can make them available by sending them to whoever wants contacting me. You can contact me either at mrys@microsoft.com, and I can send them out. Unfortunately, I don't have a place to put them. I can put the presentation up on slideshare.net, which I will be doing.
Great.
Actually, it should have been loaded by now. I did that just before we started. So if you go to slideshare.net/Michael Rees, you should be able to find that presentation within the next 5 minutes or so.
Wonderful, perfect. And if anybody sends me an email as well, and my email again is in your confirmation and your follow-up email from Citrix, I'll go ahead and forward them to you, Michael.
Okay, cool.
And Yes, this session has been recorded, and it will be available on our website at pragmaticworks.com under past webinars. And thank you so much, Michael. That was a wonderful presentation. We sincerely appreciate it. All right, everyone. Have a great weekend.
Bye-bye.
Bye.